Let's take a look at some molecular compounds. So you can see that there are different numbers of atoms in them. What we're going to do today is take a look at where do the formulas come from and where does the naming come from. And we're also going to throw in some acids and some hydrates at the end of this video. All right, so let's take a look first of all at what is a covalent bond. So covalent bonds are bonds that form when atoms share electron to complete their octets. And we only have them between non-metal atoms and nothing else. So let's take a look at, for instance, a hydrogen molecule. So if we start off with two hydrogen atoms, and they were the electron dot symbols, which you guys did earlier, so they can share two electrons between them. And this way they kind of fill up their first energy level. Here are those two electrons that they're going to be sharing. Now, these two electrons account for both hydrogen atoms for part of the time. And we can replace these shared electrons with a dash, and that's called the covalent bond, and that gives us then a hydrogen molecule. Now, this is still an element. It's not a compound, because in order to be a compound, it must have a different element with it. So H2 is simply just an element, but this is the way it exists on this planet. So all the hydrogen on this planet is H2 molecules. Let's take a look at another one. How about a fluorine molecule? So here I have my two fluorine atoms, and I put the electron dot symbols so that the unpaired ones are facing each other. So these are the ones that are going to be shared. And when they share that pair of electrons, that's our bonding pair. And we have these other electrons that are on the valence level that are not being used in bonding. And those are called lone pairs. So right now we have 3 and 3 more, 6 lone pairs. We can replace the bonding pair with that dash, and that gives us F2, a fluorine molecule. So let's take a look at a few more besides these two. So I already started off with the fluorine, and there's two other elements besides that. So the fluorine had that pair of electrons that they're going to use for bonding. If you look at two oxygen atoms, you notice that there are 2 electrons on each oxygen atom that aren't paired up. And right now, they each have 6 electrons, and we're trying to get 8, according to the octet theory. So the oxygens can share 2 pairs of electrons. So that would be a stronger situation than the 1 pair with the fluorine. And if we look at the nitrogen down here, nitrogen atoms can share 3 pairs of electrons. And that gives us these molecules. And I'm drawing in their structural formulas. We call these structural formulas. And they show the number of bonds, and they show the lone pairs of electrons as well. So we have a single, a double, and a triple bond. The triple bond is very strong, and it's hard to break that. It's easier to break a single bond than a double. Double is harder to break than that, and a triple is the hardest to break of all. How many lone pairs of electrons do they have? So we can see the 6 lone pairs here, 4 here, and 2 here. Now, interestingly, these are examples of what we call diatomic elements. This is the way they exist in nature. And if you take a look at a periodic table, you would see that 6 of them form the number 7, beginning with number 7, which is nitrogen. So number 7 goes up and down like that. That looks like the number 7. And we have hydrogen over here. So these are the 7 diatomic elements. So from now on, anytime you're writing the formula for any of these elements, you must put that subscript 2, because that's the way they exist in nature. All right, let's take a look at water. So why is water molecule H2O and not HO or H3O? We can kind of prove it using these electron dot symbols. So I take my oxygen atom and I bring over a hydrogen atom, and I bond those 2 together, and I can bring up another hydrogen atom and bond that together. And so now what we have then is a molecule of water. And thus the formula is H2O. 2 lone pairs, 2 bonding pairs. So this kind of proves that this theory anyway, the octet theory, kind of proves that this is really the makeup of a water molecule. It actually has that bent structure to it. So these structures are all called Lewis structures, named after Gilbert Lewis, who came up with this idea. So what is a Lewis structure for CO2? Let's see if we can figure that one out. So here's my carbon atom with its 4 valence electrons. Here's my oxygen atom with 6 valence electrons. Now the carbon needs 4 electrons to fill up its energy level, so it winds up with an octet. So to do that, it has to form 4 bonds. Whereas the oxygen needs only 2 electrons, so it's going to form 2 bonds. So here's my carbon atom again. Here's my oxygen. Here's my other oxygen. Now I write them so that the lone electrons, the unpaired electrons, are facing each other. Then I'm going to just circle them. I can circle this one, and this one, and this one, and this one, and then replace these electrons that I've circled with a dash, and I wind up with CO2. 4 bonding pairs, 2 lone pairs. So carbon has its own type of chemistry because carbon atoms are so versatile they can bond to each other, and they can bond all different ways. So here we have 2 double covalent bonds, but carbon atoms can form 4 single covalent bonds. It could form double and 2 singles, and it can form a triple and a single. The one thing carbon cannot do is form 4 bonds to the same atom. Now how about this one? What is the Lewis structure for CCl4? So I start off with my carbon atom, and then I bring in a chlorine, and I bring in another chlorine. Notice that I'm bringing them all in with their unpaired electrons facing each other. And then I can bond them all together. And then I would replace those shared electrons with a dash. Notice how symmetrical this molecule looks. So what do we have all together then? We have 4 bonding pairs of electrons, 12 lone pairs. Let's try another one. What is the Lewis structure for NH3? NH3 is called ammonia. So here's my nitrogen atom with 3 lone pairs of electrons. And I bring in my hydrogen atoms. Now this is why it's important that you write those electron dot symbols correctly. Otherwise you won't be able to get the right number of bonds. And so by circling the shared electrons, this time the nitrogen has 2, 4, 6, 8, and each hydrogen has the 2 electrons it needs to resemble helium. And here we go with our molecule. We have 3 bonding pairs, 1 lone pair. Now what about naming these compounds? Well, to name these compounds, we're going to have to use some prefixes. So again, ignore this table number. So what we have here are the prefixes that we're going to use in naming them. So we're going to use mono for 1, di for 2, tri for 3. Tetra is one you want to note because tetra is not used very commonly, whereas you see a lot of these others you know from geometry or even from some languages. All right, and so 4 is tetra, it's not quadro or something like that. Now one thing about mono is only used for the second element in a formula. It's never used for the first element if there's just one atom of it. So let's take a look at a couple. CO and CO2. So because carbon and oxygen form these 2 compounds, we have to have a different way of distinguishing between them than just calling them carbon oxide. So I'm going to call the first one carbon monoxide. Notice I dropped off an O in oxide so that I'm not saying monooxide. So monoxide. And then CO2 would be carbon dioxide. Looks pretty straightforward. What about these two? SO3 and P4S3. Now you have to say how many atoms of each element are present. So for the first one, SO3, there's 1 sulfur and 3 oxygens. So that's going to be sulfur trioxide. And notice then for P4S3, we've got to say that there are 4 and 3 atoms there. So tetraphosphorus trisulfide. Pretty straightforward. So here are some very common covalent compounds. Carbon disulfide, manufacture of rayon, CO2 and fire extinguishers, and beverages, NO, nitrogen oxide. Now you could call that nitrogen monoxide. I think that would be fine. N2O, dinitrogen oxide, laughing gas. SiO2, silicon dioxide, it's actually sand. Most of the sand that we find in this planet is silicon dioxide. SO2, sulfur dioxide. You smell this if you light a match. SF6, sulfur hexafluoride, electrical circuits. So that was just some examples of some common covalent compounds. Now we're going to take a look at some formulas for acids, because you might have to recognize these to write them in some equations. So these are some acids that do not contain oxygen. You may have recognized, for instance, HCl from other courses. You notice these are all called binary acids because they only have 2 elements in them, but the one element they all have is hydrogen, and the acid formula begins with it. So you can recognize a substance as being an acid if it begins with hydrogen. Now here are some acids that do contain oxygen. Nitric acid, I'm sure you've heard of this before. Nitrous acid, you see those same suffixes again. Sulfuric, very common. Sulfurous, not so common. We have phosphoric acid, and here is acetic acid, the acid that's in vinegar. Right. Now, what is a base? Again, a base is a substance that can produce hydroxide ions when dissolved in water. Well, here are some common ones. Sodium hydroxide, NaOH. This is in Drano. KOH, potassium hydroxide. This is called caustic lye. And they all can be burning to the skin if concentrated enough. We have barium hydroxide. Now, barium hydroxide gives you 2 hydroxides. You notice that's what they all have in common. So you might see compounds like this, and you want to recognize the formulas. If you see OH at the end and they have a metal in them, they're going to be a base. Now here's another compound that you're going to see in an experiment coming up, and that's called a hydrate. So hydrates are compounds that have a specific number of water molecules attached to them. Here's one, BaCl2, and there's a raised dot here in the formula, and the raised dot means that the water is bonded to that molecular compound. I should say ionic compound. So that one is called barium chloride dihydrate. So you're naming the compound as you did before. Then you're saying how many water molecules are present. And instead of saying water, you're saying hydrate. So the word hydrate means water. You hear about hydration a lot. You got to say hydrated. We're talking about water. LiCl.H2O, that's going to be lithium chloride monohydrate because there's only one of them. MgSO4.7H2O, magnesium sulfate heptahydrate, hepta meaning 7. We have strontium nitrate, and what is 4 now? We're going to use tetrahydrate. So pretty straightforward stuff. Now in the lab you're going to take copper sulfate pentahydrate, and you're going to drive off all the water and come up with just what we call anhydrous copper 2 sulfate. You're going to be checking out the mass differences and what we can get from that. All right, so here are some common names of other compounds, common and systemic. So we have water, and these are, as you look at them, they're kind of a combination of all the ones that we looked at as naming. We have water, ammonia, CO2. These 3 are all molecular compounds. Sodium chloride, of course, is ionic. Calcium carbonate, calcium oxide, calcium hydroxide, they're all ionic as well. See how you have sodium here, another ionic compound, sodium bicarbonate, baking soda. And here you have a couple of hydrates, This would be sodium carbonate decahydrate. We just had that one a moment ago, magnesium sulfate. Magnesium hydroxide, milk of magnesia. Calcium sulfate dihydrate. This is gypsum, and that's used in the manufacture of cement. So we're going to end the molecular compound video with that. So hopefully you've learned a bit, and you're going to be answering some questions from the text based on this stuff here.